So exceptions, of course there had to be exceptions, right? It's a rule, there's got to be exceptions to the rule. Okay, so one of the ways there are exceptions is if you have a molecule with an odd number of electrons. Because if there's an odd number of electrons, how can they pair up, right? There's got to be somebody left out. So these are called free radicals, molecules or ions that have an odd number of electrons in their Lewis structures. It's just not possible for the atoms to have an octet. So these, because they can't fulfill the octet rule, these tend to be unstable and reactive. So they will tend to react in a way that does complete their octets. Have you heard about free radicals before? Yeah, like in terms of health and nutrition, right? Are they good for you or bad for you? Free radicals are bad because they do unwanted reactions in your body. And so you want to avoid free radicals or things that create free radicals. So what do we do with these guys? Well, we're just going to draw the best structure that we can and leave it at that. Because Lewis model can't handle everything. So it didn't handle resonance very well. It doesn't handle odd-electron species well either, so we'll just do the best we can. So we're going to draw a Lewis structure for one of my favorite molecules. No! Right. It's all caps. And it's what you might say to the little toddlers in the lab next door when they do something they shouldn't. No! Well, it's two atoms, N and O. And then let's figure out how many electrons. Well, nitrogen has 5 valence electrons, and oxygen has 6 valence electrons. And so that adds up to 11. And we can see there's going to be trouble, right? Question? Well, nitrogen monoxide does exist. It's unstable, but it does exist. And it is one of the products of exhaust from cars in pollution. And one of the reasons it's bad is it reacts with other stuff. So we've got 11 valence electrons. Well, let's just see what we can do, right? We need 2 for the bond. 4, 6, 8, 10, 11. So as it stands now, nobody has an octet. So I think we can do better than that. So how about if we share one of the pairs from oxygen with nitrogen. And now nitrogen's got 2, 4, 6, 8. Right? This has an octet. Oxygen has 2, 4, 6, 7. Like, well, this isn't resonance, but we could put the valence electrons in a little differently and give nitrogen the odd one. And so then if we're trying to choose, we're going to place the odd electron to minimize formal charges. So looking at this, here oxygen, that's not oxygen, nitrogen. Nitrogen brings 5 electrons and is leaving with 6. So it has a formal charge of -1. And the oxygen brought 6 and is leaving with 5. And so that's +1. So the nitrogen is -1, the oxygen is +1, formal charge. And a master in chemistry, when you're drawing these structures, now that you've learned about formal charges, they'll often want you to put that formal charge on a specific atom instead of doing, well, just back up and erase them. So over here, nitrogen brings 5 and, we gotta cut this. Nitrogen brings 5 and leaves with 5. So that's 0. And oxygen brings 6 and leaves with 6, and so that's 0. Oh, well, it doesn't satisfy the octet rule, But this one at least has 0 formal charges. So that's the best Lewis structure for nitrogen monoxide. And Lewis structure would predict that that's unstable because the nitrogen doesn't have an octet. And so it's going to react with other stuff. It's going to be reactive, and that's one of the components of air pollution. Any questions? Which molecule would you expect to be a free radical? What does it have to be a free radical? Odd number of electrons, right? Valence electrons. Well, I mean, you can do this the long way or the short way. You could add up the number of valence electrons, or you can say, well, carbon has 4 and oxygen has 4. That's got to be even, right? So it's not that one. And here's carbon and oxygen again. They're both even. So when you put them together, no matter what you do, it's going to be even. Here we've got nitrogen, which is odd, 5, and oxygen, but there's 2 of the nitrogens. So we got 2 times 5 plus 6, so that's 16. That's even. Not that one. Chlorine and oxygen. Chlorine is odd, 7, and oxygen is even at 6, and so that one's got 13 valence electrons. So that's our winner. Any questions? Of course, that's not the only kind of exception. There's actually 3 exceptions. So odd number of electrons, and then we have incomplete octets. So some elements tend to form incomplete octets, right? So we've already talked about hydrogen, but hydrogen has its own rule, the duet rule. These are guys that should, we think, have an octet, but they don't. So boron is an element that often forms compounds in which it only has 6 valence electrons. And you look at boron, and boron is on the small end of the periodic table, right? 5 electrons total. So boron is a little guy. And it's these little ones that sometimes have incomplete octets because they're small and they have a hard time handling 8, right? The bigger ones, we'll find out, some of them can handle more than 8. That's the big boys. So let's draw a Lewis structure for BF3 and see what happens. I just thought of something I was supposed to do over the weekend. Totally forgot. Dang. Okay, well, probably put boron in the middle, right? And fluorines around it. You know, I don't know why I started drawing it over there. I've got this nice big space over here. Might as well use it. Boron and fluorines around it. And then how many electrons are we dealing with? Boron has 3 valence electrons. And we have 3 fluorines, and they each have 7. So that's 24 valence electrons. So we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Now, does that satisfy the octet rule? No, it does not. But let's look at the formal charges on it. So again, we're looking at breaking the bonds in half. How many electrons did fluorine bring? 7. And how many is it leaving with? 7. So this fluorine has a 0 formal charge. These others do as well because they're in exactly the same situation. Boron brought in 3 electrons and it's leaving with 3 electrons. 0 formal charges. Now, could we draw it with a double bond so the octet rule works out? Sure, we could. But now we have formal charges. These 2 fluorines are okay, because fluorine likes to make 1 bond. It's got an octet, it makes 1 bond, it's all good. The boron here, though, brought 3 electrons, leaves with 4. So brought 3, leaves with 4, so that's -1. And this fluorine brought 7, leaves with 6. That's a +1. So this is its actual fluid structure. Now, how would you know to do this one instead of that one? Because I'm telling you, boron does this. He's a little guy, right? Now, boron trifluoride does tend to react in a way that boron completes its octet, but this is a stable molecule. Another guy that does this is beryllium. So you kind of just have to remember those guys, boron and beryllium. Beryllium's over there. You might think, well, isn't beryllium a metal? Well, yes and no. So those are the little guys. We're not talking about helium, because helium doesn't form compounds with anybody. And we're not talking about, well, lithium also does an incomplete octet, because lithium doesn't form any covalent bonds. It just forms ionic bonds. So it's these little guys. Yeah. Pretty much just these 2 that'll do incomplete octets. Carbon is very steady and reliable. Carbon always makes 4 bonds, unless there's a free radical. Always makes 4 bonds, and so carbon's 4. But it's the ones that are smaller than that that can have fewer. Okay. So incomplete octet, then we have the opposite, which is expanded octets. These happen for the bigger elements. So these are the elements in period 3 and above. Now, the word above there, it means the number is above 3, not that it's above on the periodic table. But yeah, either way I say it, it's going to be confusing. But it's the big ones. These can often have expanded octets, not just 8. They can go to 10, 12, or sometimes even 14 electrons, because they're big. So let's look at a couple of these. ASF5 and SF6. So these are going to have the odd guy in the middle. So here's arsenic in the middle, and I'm going to put 5 fluorines around this. And so you just kind of have to get a little bit creative and squish them in there. And then for electrons, we've got 5 times 7 is what, 35, and then arsenic has 5. So 42? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. What happened? Counted wrong. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. Okay, something's wrong with my mind. Well, it's because 3 3 times 7 is 35, and 5 is 40. So, yeah, that's why you should use a calculator. Okay. If we do formal charges on that, everybody's 0. But it doesn't obey the octet rule. Yeah, but arsenic is in period 4. Arsenic is big, and, grown-ups, we get to disobey some of those rules that we have for the children. Well, I wanted to eat all the cookie dough. I can do it because I'm the mom, right? Like, that's never happened. SF6. I was going to have 6 fluorines around it. Sometimes, we start out with top, bottom, right, and left, and then we just squeeze. Oh, that's really ugly. We just, squeeze them in a little bit like that. Here we have 6 times 7. That's 42 plus 6 is 48. Somebody check my math. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 46. No, 44, 46, 48. Phew. So when we're doing Lewis structures in lab today, just be kind to each other, and if somebody's counting, just leave them alone. These are both stable compounds. So how do they get away with this? Well, elements in period 3, 4, 5, 6, they have d orbitals. And so what happens is the valence electrons, sulfur has 6 valence electrons, they'd be in the s and the p orbitals. They can actually expand into the d subshell, and that's how it works. We will learn the details of that in, I think it's the next chapter, or the chapter after that. Valence bond theory explains that. Let's do sulfuric acid, H2SO4. So sulfur, oxygen, 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 oxygen. For acids, for the oxyacids, the hydrogens are on one of the oxygens. So there'll be a hydrogen on that oxygen and a hydrogen on one of the other oxygens. There's just more space on the sides, so I put them there. 2 valence electrons total from the hydrogen, plus 6 for the oxygen, plus 4 times 6. It's 32. And to count the bonds first, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Nice. So what's this talking about in an expanded octet? Well, let's look at the formal charges. Just looking at this, oxygen has 2 bonds here and 2 bonds there. But this oxygen only has 1 bond. That's going to have a formal charge. So it's going to leave with 2, 4, 6, 7 electrons. It brought 6. So that's going to have a formal charge of -1. Right? And then this other one down here is also going to have a formal charge of -1. The sulfur in the middle, sulfur had 6 valence electrons, and it would leave with 1, 2, 3, 4. So this has a formal charge of +2. So that's not so great. Let's see if we can get 0 formal charges. Sulfur's in period 3. It can expand its octet. So how could we lower the formal charge on this oxygen? We could put this lone pair and make it a bonding pair with the sulfur. Then we'd have 2 bonds for the oxygen, and then when we count up how much is leaving, it would come out to be the right number. So I'm going to remove that bonding pair down here. It violates the octet rule, yes. But sulfur, as a grown-up, it can violate the octet rule. So how does that affect this? Yeah.
How do you know when you're
Period 3. Yeah. So period 3, so that would be, well, aluminum's a metal, but silicon, phosphorus, sulfur, chlorine, those guys, and anyone who's bigger,
not
larger. Aluminum is a metal. It could expand its octet, but we won't really see it forming covalent compounds. But yeah, you gotta be bigger than neon. Be bigger than neon. So period 3, you have to have d orbitals, is what it comes down to. And if you have electrons in the 3rd shell, in the 3rd level, you've got d orbitals. So this oxygen now, we messed with it, so its formal charge is probably different, right? So it would leave now with 1, 2, 3, 4, 5, 6. So that would be a formal charge of 0 on that one. And what about the sulfur? Yeah, the sulfur's formal charge has gone down to +1. So that's better, right? Well, that worked out really nicely for this oxygen. Could we do it with this oxygen? Yeah, we could. So I'll move a lone pair to become a bonding pair. And then this is going to have a 0 formal charge. And now what about the sulfur? 0 formal charge. That's the Lewis structure for H2SO4. So you should have learned about Lewis structures in Chem 3A, or your previous class. They probably did not talk about expanded octets and formal charges, definitely they didn't talk about in 3A. So period 1, period 2 elements never, ever, ever have expanded octets. So carbon, nitrogen, oxygen, fluorine, you can't do this. Bigger ones, yeah, it's possible. And we use formal charges to help us decide, well, should I expand the octet or should I not? Any questions? Well, we would like to get all the formal charges to be 0.
Oh, not the sum of them should be 0.
Right. The sum will always add up to the overall charge on the molecule or the ion. That will always be true. And so if you want to add them up to see overall, or am I getting smaller formal charges, you can add the absolute values of them to get a total, but just simply adding them doesn't help. But we want to get 0 if we can, 0 on everybody. Because this is, if you think about this business model idea, everybody came in and I brought 1 electron, he brought 6 electrons, and we made this corporation, and now we're breaking it up, and we're all going to break even on it. We're going to leave with what we came in with. It's all nice and fair, instead of one person getting extra and another person losing, if that helps you remember. Sometimes it's not possible, but then you want to minimize the discrepancies, right? Write the Lewis structure for XeF4, so it'd be xenon tetrafluoride. thought noble gases didn't make compounds. Well, they do, just not very many. And it's the bigger ones that do it more. Helium does not. Okay, well, how many valence electrons do we have here? Xenon has 8, right? And we have 4 fluorines, and they each have 7. So that's 28 plus 6 is 36. Check me on that. Tell me if I got it wrong. So 2, 4, 6, 8. Who do we appreciate? Yeah, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Ah! Everybody has an octet. I put 32 electrons in. I'm supposed to squeeze 4 more electrons in there. This is the opposite problem we've usually dealt with. Who do I give the extra electrons to? Who can expand its octet? Xenon. Well, how do I do that? Well, just put some lone pairs on it. Yes, it's going to look funky. But when we look at the formal charges here, we find out, oh, well, everybody's got 0 formal charge in that. It's all good. I know if you thought you had a good handle on Lewis structures, I might have just rocked your boat. Sorry. Any questions about that one? Yeah.
Why did you put the lone pairs?
I put the lone pairs on xenon because xenon is a big boy, right? Can expand its octet. Fluorine cannot expand its octet. So regardless of formal charges or anything else, the only place I could put them would be as lone pairs on the xenon. Yeah. Okay, H3PO4. There's another one of those oxyacids. So phosphorus and the oxygens around it. And then really just because I told you, the hydrogens are each going to be on an oxygen. Just, to save you doing all the other permutations that are possible. So each hydrogen has 1, and phosphorus has 5, and oxygens have 6. It's 24 and 8, that's 32. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Yay! Came out even. But wait, there's more. Does everybody have a 0 formal charge? We can tell quickly by thinking about how many bonds do these elements like to make. Oxygen likes to make 2 bonds. This oxygen has 2 bonds. This one has 2 bonds. This one has 2 bonds. Uh-oh. That one only has 1 bond. That's going to have a formal charge. So it brings in 6. It leaves with 2, 4, 6, 7. So that would be a -1 formal charge. And phosphorus in group 5 likes to form how many bonds? Just like nitrogen, 3. But here it's got 4 bonds. That's going to have a formal charge. So phosphorus brings in 5 electrons and it leaves with 4. And so this is going to be a +1 formal charge. Yes? It likes to form 3 bonds because if I draw the Lewis structure for phosphorus, it has 5 valence electrons. 1, 2, 3, 4, 5. And so put 1 on each side and then pair up as needed. I have 3 unpaired. That predicts 3 bonds. That's a little bonus that's not in the book. Okay, so Could we lower those formal charges to 0? Well, can phosphorus handle more than 8 electrons? It can. So let's do that, because this negative formal charge on the oxygen is saying that oxygen's got a little too many electrons. So we want to shift this to get some away from the oxygen. So I'm going to shift a lone pair from the oxygen to become a bonding pair. Oxygen still has its octet. But now when we look at formal charges, it's only going to take half of those. 1, 2, 3, 4, 5, 6. It came with 6, and so it's got a 0 formal charge. The phosphorus brought 5 electrons in, and it would leave with 5, and so it also has a 0 formal charge. So by expanding phosphorus's octet, we can get 0 formal charges. Any questions? Yes? Yeah, so is there a way to indicate on the structure that we've expanded the octet? We don't need to, because we can look at it and see, oh, well, phosphorus has 10 valence electrons. 10 electrons in this structure. It's an expanded octet. Yeah, so there's no special notation or anything. Boy, this lecture's running long. Any questions?